Okay, so to continue on with the notes, I'm just gonna go through a couple review things and then some new measurements that we'll need to make in our identifying glass lab to solve our little mini case. Okay, so we've talked about and you've read about and watched videos on how glass is made. It's made from sand as the primary component, but there are other things like soda ash and lime that's added into the batch. Different types of glass have different substances added to it. We call that dope, and that dope gives it unique properties. So sometimes those can be different salts with different colors. They can be different things like borosilicates that can change the properties of the substances. So just kind of to recap a couple of them, we talked about float glass. It's very uniformly flat. There was a whole video on the process of how float glass is made. Other types of glass, so a big one that we use in our chemistry laboratories is Pyrex, also known as borosilicate glass. Key property of this is that it's heat resistance. This allows it to be used in cooking. It's great for thermometers, headlights, anything that really has a lot of changing in temperatures or gets really hot. This type of glass is great, like I said, in chemistry equipment, glassware that we use. Then there's tempered glass. This is a type of safety glass. It's a very strong glass. It's often found on car windshields or like the side glass, so side doors and back door. It's not found in the front just because it does break into small pieces, and so really want glass that's kind of held together for the front windshield. It is a very strong glass, though. It's like 4 times stronger than regular glass. So it's a lot harder to break, but when it does break, it shatters into small pieces. This is good. We don't want sharp pieces when it breaks because those can, act as daggers and go into the body. So that's why it's also a type of safety glass, but it's more expensive. And then another type that you learned about was laminated glass. This is an interesting type of glass. It's really 2 layers of glass with a layer of plastic fused between. This is the type of glass that's used in the front of a windshield. So if you've ever seen like videos or something, and there were videos of this, the way that they break these different types of glasses break differently. But it shatters, but it stays connected. So you get more of that like indented baseball bat look to the glass, where the glass hasn't broken up into small shards. So this is another type of safety glass. There were obviously other categories of glass that you read about and learned about and took notes on, so I'm just kind of recapping a few of them. So besides the types of like trying to figure out what type of glass something is, so maybe it's bulletproof glass or maybe it's mirrored glass or soda ash glass or any of the other ones from the list that you got from that first video, other things that we can look for would be just the characteristics with our eyes that we might see or with a microscope that we might see in the glass. So we might notice a color to the glass or a fluorescence. Sometimes glass is clear, but then if you look at it at a certain angle, it has like a bluish tinge or a greenish tinge to it. So it has a particular fluorescence to it. Sometimes like this glass here, it could be red or it could be orange or it could be painted. So those would be characteristics that would allow us to identify glass. Texture, we can see here that this glass is bumpy. Sometimes it's smooth. Sometimes it's, if it's created in a unique way where maybe it causes it to have effects in it, like a kind of a cracking appearance, or sometimes it has like a little bubbling appearance in it. Those would be all unique textures that could be generated in the glass. Thickness, right? Thickness can be uniform. In other words, like with float glass, its thickness is exactly the same all the way throughout. Whereas sometimes you've got, like if it's a bowl or a cup or a glass bottle, so those types of soda ash glass can be molded and shaped in different ways, and so the change in thickness can be identifying characteristics for that glass. Shape, right? So it kind of goes along with thickness, if it's completely flat or if it has curves to it. So here, obviously, the fact that this glass on the edges would be curved and polished and smooth could be something that could allow us to identify its source, or at least its group that it might have come from, that it's windshield glass, or that it's headlight glass or taillight glass or something like that. Any surface features or markings, sometimes there's stamps that are put into glass, there's, if it's our chemistry glassware, then there might be, markings on there for the graduated, scale on the glass. Sometimes there's, if it's a coffee cup, then there would be words or any, descriptions in the glass itself. The fit of irregular pieces. So this is where we get, where we might have match fit. And if it's unique enough, then this would allow us to possibly take what was once just class evidence, and as long as it's very unique and very irregular, and we can only really statistically say that one piece could have really fit into this known source, then we might be able to individualize glass. So taking the fit of pieces and being able to match them underneath a microscope and see that their fracture lines all line up exactly. That might allow us to individualize glass. Otherwise, most of the time we're just able to identify it and put it into different class evidences. But if we have unique enough pieces, we might be able to individualize it to an exact source. Chemical composition, this would be helpful class evidence. We don't have the equipment to do this, but we could, take glass samples and analyze them using equipment that can actually detect what chemicals were used in making the glass. And that would be another helpful class evidence. Density is something that we can do in the lab, and so that's where the next couple slides I'm going to talk about density and how we would do that in the laboratory. Density is a property of really all matter. So if it's made up of a certain composition, then we can calculate the density of that for the substance. So for instance, Pyrex would have a particular density range versus maybe lead glass, which would have a different density range. So or optical flint glass has a different density range. So we could use those density properties to help identify the class of glass that we have. Another thing that we could use is what's called refractive index. And again, we'll talk more about that in just a second. But refractive index is the way that light bends when it enters through glass. And so different glass substances will have a different refractive index measurement. And we can use that to help us identify the class of glass that we have. So let's focus on density. So density is... Again, here's some examples. Pyrex has a range here from 2.23 to 2.36. Porcelain has a range from 2.3 to 2.5. So we can see sometimes they're overlapping, so it wouldn't be enough information maybe if we had something that was 2.5 to know which of these it specifically was. But if we combine that with the color, if we combine it with refractive index, if we combine it with, the textures, then we might be able to figure out more about the glass. So it's really a combination of using density with the other identifying characteristics. Window glass, again, 2.46 to 2.49. So if we've got a piece of glass that is in the 2.46 range, it could be window glass, but it could also be porcelain. It's likely not Pyrex. It's likely not lead glass, and it's likely not headlight glass either. So we've narrowed down that range. Density, by definition, is the amount of matter, which can be measured as mass, that is packed into a given space, which we can measure that as volume. So all materials that are made of different substances can have different densities that can be helpful in identifying them. Glass with the same thickness and overall transparency or appearance may have different densities, or they could have the same density, and this could allow us to identify whether a known and an unknown are from the same or similar source. So how do we actually get the density of glass? The first thing we need to do is measure the mass of the glass using a balance. So if we've got a piece of glass, walk over to the balance. We want to make sure that the balance starts off at 0 always. Otherwise, we might be getting a false measurement. So there's usually a button on the scale, and one of these buttons would be what's called a 0 button. So you're zeroing out the scale, or even a tare, T-A-R-E button. Sometimes just a capital T or a 0 on there. But when you push that button, then this will go to 0. Even if something was sitting on it, it would still go to 0. And then whatever you add to it, always make sure that you zero out a scale before using it. Otherwise, you're going to get a false measurement. Place the piece of glass on here, and then whatever the measurement records as, that's the mass of the piece of glass in air. So then we would record that. The next step is we need to measure the volume. There's actually 2 different ways that we can measure the volume. One of them is pretty easy, but not always an option. So the first thing that we can do is measure the volume of water that is displaced when adding an object to a graduated cylinder. This is called the displacement method, and I'm sure you're aware of this. Do this in elementary school a lot, but so if you've got a certain volume of water, so here it says that the water is 50 milliliters, and then I place an irregular object, like a rock in this case, in here. And we could do this with glass. As long as the glass fits into the graduated cylinder, then this will work. Often, though, our pieces of glass are so big that they might not fit, and so then this process would not work. Or sometimes they're too small that you don't see enough of a change in, a change in a half a milliliter. You wouldn't really be able to detect that. And your numbers wouldn't be precise enough. But this is how this process works. Basically, you've got 50 milliliters of water, you add an object to that water, and it displaces or pushes the water out of the way. Well, how much water was displaced is obviously is equal to the volume of that object. So in this case, because the irregular shaped object displaced 25 milliliters of water, right? So move 25 milliliters of water upwards out of the way, then that tells us that the irregular shaped object has a volume of 25 milliliters. That's the displacement method. The second method, which you will use most likely in all of your pieces of glass, is a little bit trickier. Basically, you're going to start with a scale, and you're going to place a beaker of water on the scale, and then you're going to want to zero that out. So that way none of the apparatus is being measured as mass. So you're going to start by zeroing this out. And then what you're going to do is, the whole point of this is to measure the change in the mass of the water that's displaced when that piece of glass is suspended in it. So the setup's going to look a little different. So once you have this set up, there will be a ring stand also behind here. And what you're going to do is make sure that this is set to 0, because again, you don't want to measure any of the equipment that's on there. And you're going to then hang, basically, if this is your piece of glass, you're going to hang it from a piece of string into that beaker of water. And then this is the balance tray. So the piece of glass that's hanging here will displace a certain amount of water, and that will get recorded as a mass measurement. Now in this case, though, we're not actually measuring mass because the piece of glass isn't actually touching any of the sides. So really what it's doing is it's displacing a certain amount of water, and because water is 1 gram per milliliter, then we know that that is the amount of water that's displaced is the volume of that piece of glass. So just to kind of recap, so when the glass was not in the water, then this should all have read 0. Then we hang this piece of glass from a thread, and it'll be hanging from a ring stand, and the glass will be hanging suspended in the water, and the mass readout will increase. So it should go up, depending on how big the piece of glass is, but maybe it goes up to 1.46. Then that actually tells us that the volume of that piece of glass was 1.46 grams. It's really important that you remember that the piece of glass can't be touching anything. So it can't be it has to be completely underwater. It can't be half in, half out. And it can't be touching the sides or it can't be touching the bottom of the beaker. It has to be completely suspended. And then we'll get a pretty accurate measurement of the volume of that piece of glass. And that volume would be in milliliters. So the mass measurement will be in grams. The volume measurement, depending on which method we use, would be in milliliters, most likely. Then the third step is to basically calculate the density. And we calculate the density using mass divided by volume will give us our density. And so our units for density would be grams per milliliter would be the units for density. And that's how we would get a density readout. The next thing that we can do to identify glass is called refractive index. So refractive index is another thing that tells us about a piece of glass. So remember you read about different types of glass. So quartz glass, I think you read about flint glass, which is a type of glass. There's other mediums here that light passes through, so they've listed them here. And refractive index, so space, there's a refractive index of 1, which gives us the speed of light. But when light passes through air, it changes the speed of the light changes slightly as it's moving through air because air has molecules in it. If it's moving through water, then the speed of light changes, and so that changes its refractive index value. Okay, so different substances have different refractive indexes. We're not going to get as complicated as measuring this value, but we're going to be able to make comparisons based on that. So you can see here when the light is passing through just air, it's traveling at a certain speed, but then when it hits a piece of glass, the speed changes, and then so it's bending the light, and that's what refraction is. And then when it hits the air again, it can change its speed again because now it's passing through a medium that's easier to move through, and so it bends it again. So again, the refraction is happening here at these spots. It's causing the light to bend. So again, refractive index is the measure of light bending as it changes speed from one medium to another. Different materials have different refractive indexes. So how can we actually measure refractive index? First, we need to know what Beck lines are. So Beck lines are basically a bright white halo-like light that appears around an object immersed in a liquid with a different refractive index. So here's an example. We've got this liquid out here, okay? And then we have this piece of glass. And we put the piece of glass into the liquid. Now the liquid has a refractive index of 1.525. The piece of glass has a refractive index of 1.60. Because the piece of glass has a higher refractive index, it actually forms a Beck line on the inside. That white halo-like appearance ends up inside the glass, not inside the liquid. Okay, so the rule of thumb is whichever substance, the glass or the liquid, has a higher refractive index, that's where the Beck line will be. So let's take a look at this example over here. Right? So again, on the left, the Beck line is in the glass. So that means that the refractive index must be greater than the glass refractive index must be greater than the liquid refractive index, which it is. So we're kind of working backwards because we know the refractive index is here. On this one, we can see that the glass, so it's a different type of glass that's been placed into the same liquid. So the liquid is still 1.525 refractive index. So we know this value, and we place this piece of glass in there, and we would expect that the liquid would have the Beck line because it has the higher refractive index, and we do. We see the white halo-like line ends up on the outside. Now you have to be careful because sometimes students will look at like these fragmented areas and see these white halos here, but that's because the light's being scattered along these breaks. So you really want to find a flat, kind of smooth area. So sometimes it's a little bit harder over here. So I wouldn't necessarily look in this edge because it's, it gets a little bit confusing where the breaks are happening. I would tend to focus on a nice straight edge when you're looking for those Beck lines. And again, because the Beck line is in the liquid out here, that's where you're seeing that white halo, then that would tell us that the glass must be less, it must have a refractive index that is less than the liquid's refractive index, so less than 1.525, which again, in this case, we know the glass is 1.34, but we won't know that if we're looking at an unknown piece of glass. Match point is when the refractive index of the liquid matches the refractive index of the glass, and there is no Beck line. So what's interesting about match point, so if I took a piece of glass and I put it in here, and that piece of glass had a refractive index of 1.525, the piece of glass would basically appear to disappear. Like it will become invisible. A lot of magicians use this trick. Because the glass will no longer be visible to the eye, because no light will be changing, so it'll be basically kind of passing through both mediums at the exact same speed, so you won't be able, since they're both transparent liquids, or transparent substances I should say, you won't even be able to see the solid glass inside the liquid. But that's only if they have a match point, which means that the liquid and the glass have identical refractive indexes. So here's just a slide to kind of help you understand this again and just kind of go back through this. So when we're estimating the refractive index of a glass sample using a microscope, we do this. So we use different types of microscopes can be used. We'll probably actually use a stereoscope for ours just because our glass samples are big. And if you don't see any Beck lines, and again, we're kind of imagining that we see a piece of glass, but we can't see the piece of glass, the glass seems to disappear, then that would mean that the glass and the liquid have the same refractive index. So if we're using a liquid that we know has a refractive index of 1.7, then the glass must also have an index of 1.7 in this case, and this would be match point. If the glass has a higher refractive index, then again, we're going to see that the Beck lines are in the inside of the glass. And then if the liquid is the one with the higher refractive index, then again, we would see the Beck lines, the halo-like appearance is going to be on the outside in the liquid. So looking at these and kind of applying what we just learned, right? So if the refractive index here is 1.54, we can see that there's Beck lines on the outside of the glass in the liquid, not in the glass, but in the liquid portion, then that tells us that the refractive index of the glass must be less than 1.54, and it turns out that it is. It's 1.51 to 1.52. So for this type of glass, we kind of know the answer already. If we're looking at this one here, hopefully, and again, just kind of practice looking at it, you can see that the Beck lines are in the liquid again. So again, don't look at like the fracture areas. Those can be harder to tell. You want to look on the edges, kind of where it's smooth. So this is a nice straight line. That's a good place to look. Out here is a good place to look. Even over here is a good place to look. So we can see that. And you also kind of want to look at the whole thing. Like I said, if it's like broken on a certain edge, then it might be harder to read. This edge here is a little bit harder to read. So these pieces of glass definitely would have a refractive index that's less than the liquid. So the liquid has the higher refractive index. Whereas if we're looking at this one, the Beck line is on the inside of the glass. You can see that halo-like appearance. This over here is really hard to look at, so you can't always look at the whole piece. You kind of want to look at the overall. It looks like the majority of the Beck lines are on the inside of the glass, which would mean this has a higher refractive index than whatever liquid we put it in. Here, and again, this just kind of shows you different microscopes are going to look a little bit different, but if I'm looking at it, I see that halo-like effect is in the outside, it's in the liquid. So here's another piece, and I want to keep, these are all the same type of glass, and I want to keep, looking at them, different ones, but it looks like the halo is in the liquid again, so it's similar to these two, where the liquid has the higher refractive index than the glass. So a lot of times we use known refractive indexes to help us to identify what type of glass we might have. So using this chart here and some information that we gather. So which liquids, so if we've got this piece of glass and we think it's bottle glass, then we'd want to choose certain liquids in order to help us to identify whether or not it is bottle glass. So if I'm looking at this chart, I see that bottle glass has a refractive index of 1.51 to 1.52. So I want to choose a liquid that would help me to figure that out. So something I could use would be the vegetable oil. So if I go over here to vegetable oil, it has an index of 1.474. And so when I put the bottle glass in there, then the bottle glass should get the Beck lines. But then if I use clove oil and I put the bottle glass in the clove oil, then the clove oil should get the Beck lines. So by choosing these two liquids, it could help me narrow it down. So if I choose Wesson vegetable oil and the Beck lines were actually in the oil instead, then that would tell me that actually it can't be the bottle glass, because that would mean that it has to be less than 1.474. But if I put the glass into the Wesson vegetable oil and indeed the bottle glass is the one with the Beck lines, then that tells me it's got to be greater than 1.474. Then I put it in the clove oil, and again, if it does fall within this range here, which bottle glass should, so does optical though. So it doesn't 100% tell me what it is, because window glass would also fall within those ranges. But if I'm trying to see if it is indeed bottle, or if it could possibly be bottle glass, then I would need to use these two to get the narrowest range. Obviously, if I didn't have Wesson vegetable oil, I could choose other ones, but if I'm trying to get the most narrow range, I want to choose the two that would basically be below and above that, the one I'm investigating. The second one, which liquids could help identify headlight glass? So headlight glass is 1.471. So I would choose olive oil and glycerin, because that would be below and above this 1.471. So the headlight glass, when I put it in the olive oil, the Beck lines, if it is headlight glass, then the Beck lines would be in the would actually be in the glass. And if I put it in glycerin, then the Beck line should be in the glycerin, and that would tell me that I'm looking at something between 1.46 and 1.47. 473. Which liquids could help identify quartz glass? So quartz glass, if I'm looking over here, 1.544 to 1.553. So if I used clove oil and bromobenzene, then this range would fall in between there. And again, if I place this quartz glass, what I think is quartz glass, into the clove oil, the Beck line should be in the quartz glass. If I then place it into the bromobenzene, then the Beck line should be in the bromobenzene, and that would tell me that this is definitely something with an RI between those two. Which liquids could help identify Pyrex glass? Pyrex is 1.474. If I look for the range here, so Wesson vegetable oil, I could use glycerin and Wesson vegetable oil or clove oil, but the thing is this is Pyrex is an exact match to Wesson vegetable oil. So if I put the Pyrex in the vegetable oil, the Pyrex should disappear because it would be at match point. So it should appear to no longer be there. And so vegetable oil should give me a for sure that if I place this piece of glass that I don't know what it is, but it might be Pyrex, into the vegetable oil, and it reaches match point, in other words, there's no bending of the light, I can't see the object anymore, then I know that I have a substance with a RI value of 1.474. And something that has an RI value of 1.474 is Pyrex. So it's likely or possible that it is indeed made out of Pyrex. Whereas if it was actually headlight glass, then the Beck line would be in the vegetable oil, and I'd still be able to see that glass. Okay, so continuing on, so I have a piece of unidentified glass and it's placed in clove oil. and the Beck line is observed in the clove oil. What does this tell us about the unknown glass? So again, a piece of unidentified glass, so it's one of these types, right? But again, I'm not trying to necessarily, just trying to figure out what it tells us about the unknown glass. So I put it in clove oil, and the Beck line is observed in the clove oil. That tells us that that this glass must be less than 1.543. So if I know it has to be one of these options, and there's quite a few of them it could be. All that tells me is that it's less than 1.543. So it could really be any of these are all less than 1.543. But it narrows it down. I now know it's not any of these. Well, any of these here. I know it's not quartz, lead, diamond, or Pyrex. Nope, I lied. It could be Pyrex still, because Pyrex is 1.474. Number 9, a piece of unidentified glass is placed in bromobenzene, so go to bromobenzene, and the Beck line is observed in the glass. What does this tell us about the unknown glass? It tells us that the glass has a higher index, right? The glass refractive index is greater than 1.560. So it could be lead, it could be diamond, and out of this list, that's it. But again, the list of glasses are a lot longer than this. So, number 10, a piece of unidentified glass is placed in olive oil, and the glass seems to disappear. What does this tell us about the unknown glass? So we placed it in olive oil. That tells us that it must have an RI value, that piece of glass, equal to 1.467, because it is reaching the match point, and that's why the glass appears to, or seems to disappear. So it must have an RI value of 1.467. Okay, so those are so kind of an analysis of how we will do density, the steps that you would use, and then also how we will look at RI values and be able to determine a little bit more information about an unknown piece of glass.